Welcome back, everybody. Today, we're going to give a brief introduction to the Hecke algebra, and we're going to look at it from several different perspectives. Okay, so first, we're going to try to turn the set of isomorphism classes of correspondences into a Z algebra. So let's let X be a smooth projective curve, and we'll denote by core X the free abelian group on the set of isomorphism classes of correspondences on X, where we say two correspondences Z1 phi1 psi1 and Z2 phi2 psi2 are isomorphic if Z1 is isomorphic to Z2, of course, and the associated pairs of morphisms phi1 psi1 and phi2 psi2 form the obvious commuting triangles with the isomorphism from Z1 to Z2. So I'll let you draw all that out yourself. I'm going to go over these details here quickly because they're not super important conceptually. Okay, if T equals Z phi psi and T prime equals Z prime phi prime psi prime are correspondences on X, you can define a product of isomorphism classes T prime with T in the following way. So take the isomorphism class of T prime and multiply it by the isomorphism class of T in the following way. You're going to take the sum over W, I'll describe what the sum is over in a moment, of the isomorphism classes of W tilde, which will be the normalization of W, comma, phi compose per Z compose V sub W, comma, psi compose per Z prime compose V sub W. Now, what's going on here? So here, W runs over all the irreducible components of a certain subset of Z cross Z prime, which we'll call Z double prime. It's the set of all ZZ prime such that psi of Z equals phi prime of Z prime. Here, V sub W is a map from W tilde to W. It's given by the normalization map. Every normalization of any variety comes with a special map from the normalization to the variety itself, equipped with certain special properties, basically. This is an algebra geometric concept. And then these per Z and per Z prime maps, they're projections like you might have thought they were. So per Z is just the map from Z double prime to Z, and per Z prime is just the map from Z double prime to Z prime. Okay, so those are just the projections on the product here. Okay, now you can extend this product to core X just by Z linearity. Okay, and so what happened, the upshot of this entire discussion is that core X is a Z algebra, not merely just an abelian group. Okay, so to recap, the set of all isomorphism classes of correspondences on a smooth projective curve is a Z algebra. Okay. All right. Now we can also recall, we've talked about this before, you can view aught X as a subgroup of the multiplicative group of core X by taking any automorphism psi and identifying it with the automorphism class of the correspondence X, identity on X psi. So basically every automorphism of X can be thought of as a correspondence, or more precisely, a correspondence isomorphism class with this new terminology, because you can view an isomorphism, let's say psi, as a correspondence X, and the two maps in the correspondence are psi and IDX. Okay. So let's specialize this discussion to X sub 1 of n. We want to study the subalgebra of core of X sub 1 of n, generated over Z by the isomorphism classes of all the Hecke correspondences TP and all the diamond automorphisms diamond of D. We'll denote this subalgebra by kind of a script T here. It's called the Hecke algebra of level n. Okay. We'll also denote by T the image of T under the canonical embedding from core of X sub 1 of n to end of the Jacobian of X sub 1 of n, denoted J sub 1 of n. This comes from a discussion in a previous video after the main theorem of elliptic curves. We talked about how correspondences on curves admit endomorphisms of Jacobians. Okay. We can also identify the opposite algebra T op, so that's just T with arrows reversed, with its image in end of omega 1 of X sub 1 of n. We've talked about this already. Things in the Hecke algebra admit operators on the space of holomorphic differentials on the corresponding curve that we're dealing with. So we've dealt with this recently. Yet another way of thinking about T is we can view T as acting on the dual space of omega 1 of X sub 1 of n, because every action admits a dual action. Or finally, we can view, if we don't want to reverse arrows, we can consider T as acting on omega 1 of X sub 1 of n on the right instead of on the left. Okay, so that I just gave you like 5 ways of thinking of the Hecke algebra. Okay, now it's this last kind of group of perspectives here that we're most concerned with, because it's consistent with our identification of omega 1 of X sub 1 of n slash C with S2 of n. We had that canonical isomorphism in previous videos. And so we can view T as a subring of endomorphisms on S2n because of this isomorphism, generated over Z by the Hecke operators T sub P and the diamond operators diamond of D on S2n. Instead of thinking of TP and diamond of D as correspondences now, we're thinking of them as operators on the space of weight 2 cusp forms for gamma 1 of n. Okay, now because you can do this, because you can view T as a subring of endomorphisms of S to N, T must be commutative because all these guys commute with each other. Okay, and so in particular, T is just canonically isomorphic to T op, and every left T module is a right T module. Okay, and so T is actually a fantastic little algebra once you view it as an algebra of operators on S to N. Okay, so next time we will push towards connecting this concept, the concept of the Hecke algebra, to modular abelian varieties. So I'll see you then, and thanks for watching.